In this section, we will discuss metals. Metal atoms have low ionization energies. As a result, in solid-state metal, the atoms lose some of their valence electrons to form cations. The delocalized electrons are free to move inside the entire solid. They are called free electrons and form a so-called electron gas, or electron sea in the metal. The free electrons are responsible for many properties of metals. For example, free electrons tend to drift when acted upon by external electric field, making metals good electric conductors. The opacity and luster of metals are also the results of their electric conductivities. Free electrons carry thermal energy as well. So, metals are also good heat conductors. For example, the heat sinks for CPUs are usually made of copper or aluminum. In metals, the atoms interact one another primarily with metallic bonding. Metallic bonding is the electrostatic attraction between the metal cations and free electrons. Meanwhile, covalent bonding also exists in metals. For example, gallium crystal has orthorhombic structure. It is caused by the directional covalent bonds between gallium atoms. Metallic bonding even exists in liquid metals. Therefore, metals maintain their electrical and optical properties in liquid states. For example, liquid mercury has very good electrical conductivity and luster. The metallic bonding is very strong. As a result, metals often have high boiling points, with tungsten being the highest of all elements. Even though gallium will melt from the heat of one's hand just above room temperature, its boiling point is not far from that of copper. Metallic bonding in liquid metal demonstrates that the metallic bond is lack of directionality and is best understood in contrast to the directional bonding of covalent bonds. The freedom of electrons to migrate gives metal atoms the capacity to slide past each other. The bonds can easily be broken and replaced by new ones after a deformation. This process does not affect the communal metallic bonding very much, which gives rise to metals' characteristic ductility and malleability. Ductility refers to the ability of a material to sustain significant plastic deformation before fracture. Malleability is characterized by a material's ability to deform plastically without failure under compressive stress. For example, the most malleable metal is gold. Gold can be hammered to form a foil of a thickness of a few layers of atoms. An alloy is a mixture of chemical elements of which at least one is a metallic element. The metal with the highest fraction is usually called the base metal. Alloying elements are well controlled to produce desirable properties. Impurities usually denote undesirable elements. For example, in carbon steel, iron is the base metal, carbon is an alloying element, and sulfur is considered as an impurity. In an alloy, the atoms are joined by metallic bonding rather than by covalent bonds, ionic bonds, or van der Waals forces. Therefore, alloys have metallic properties like electric conductivity, luster, and ductility. Alloys often have properties that differ from the base metal. Most metals used for commercial purposes are alloyed to improve their properties or behavior. For example, stainless steels are stronger, harder, and more resistant to corrosion than pure iron. Metals may also be alloyed to reduce their overall cost while maintaining the properties. For instance, the alloys of gold and copper is cheaper than gold, but still looks golden. When the atoms of base metal and alloying element are relatively similar in size, some of the atoms composing the metallic crystals of the base metal are substituted with atoms of the alloying element. This is called a substitutional alloy. Examples of substitutional alloys include bronze and brass, in which some of the copper atoms are substituted with either tin or zinc atoms respectively. In brass, copper typically has the larger proportion, generally 2/3 copper and 1/3 zinc. The high malleability and workability, relatively good resistance to corrosion, and traditionally attributed acoustic properties of brass have made it the usual metal of choice for construction of musical instruments. If the size of the atom of the alloying element is much smaller than the base metal and cannot successfully substitute them in the crystal, the smaller atoms become trapped in the interstitial sites between the atoms of the crystal. This is referred to as an interstitial alloy. Steel is an example of an interstitial alloy because the very small carbon atoms fit into interstices of the iron crystal. The carbon atoms form additional bonding with iron, making steel much harder and stronger than pure iron. As the carbon content rises, steel becomes harder and stronger but less ductile. Stainless steel is an example of a combination of interstitial and substitutional alloys because the carbon atoms fit into the interstices, but some of the iron atoms are substituted by nickel and chromium atoms. 304 grade stainless steel, also known as 188, is commonly used for kitchen utensils, pans, knives, and forks. It has an alloy consisting broadly of 74% iron, 18% chromium, 8% nickel, and less than 0.08% carbon. Chromium and nickel add strength and hardness to iron, but their main function is to make it resistant to rust or corrosion.